So we've compared and contrasted characteristics of acids and characteristics of bases, and in a lot of cases they're sort of the flip side of one another. Now in the next chapter we'll talk about pH, and we'll hopefully get to do some titration stuff, but for now you just kind of have to be satisfied with these characteristics. And remember, characteristics are not definitions. We're about to start into definitions of acids and bases. These are just things they all have, that all acids have in common, things all bases have in common, but they're not definitions. So there are three common definitions for acids and bases. We're going to talk about two of them. And the first one we're going to talk about is this Arrhenius, acids and bases. This is the oldest working definition for acids and bases that we have. This one dates from, I believe, the 20s. Danish chemist, I think, maybe. I could be wrong about that. But it's old. This is relatively old in terms of acid definition. It's still applicable, it's still used, and it's probably, if you've learned any kind of definition of acids, this is probably the basics of what you've learned. So this actually forms the basis of the pH scale. So your experience with acids and bases would really be based on the Arrhenius definition, whether or not you know it. So the Svante Arrhenius, I think he was Danish or Swedish. If something increases the concentration of hydrogen ions, our little naked protons, in a solution, it is an acid. Okay? So if you have a substance and you put it into an aqueous solution and suddenly you generate a bunch of hydrogen ions, except of course we know that they're not really hydrogen ions. What do they really form the minute they get into an aqueous solution? Really what? H3 hydronium. Yeah, H3O1 plus. So not really hydrogen, really hydronium. But if something increases the concentration of hydrogen ions or hydronium ions in a solution, then it's an acid by this. You think, well, okay, if it increases, it's an acid, it must be if it decreases, it's a base, right? No. If something increases the concentration of hydroxide ions in a solution, by this definition, then it's a base. Okay? So if it increases the concentration of hydroxide ions, it's a base. If it increases the concentration of hydrogen or hydronium ions, it's an acid. So do you see how we could have higher numbers still meaning a base? Because we're still increasing something in bases. Make sense? Okay. This is the oldest working definition. It's still used in some ways, but for the most part we have kind of gotten away from this definition and we've gone on to some newer ones. So if you think back to the last chapter, we talked about solutions that conduct electricity. What are those called? Electrolytes, electrolytic solutions. And we talked about the fact that some solutions conduct electricity better than others. What do we call solutions that conduct electricity really, really well? Strong electrolytes. What do we call solutions that conduct electricity? Meh. Weak electrolytes. Okay. Well, we know that a lot of acids conduct electricity. And we can kind of take a corollary from those strong and weak electrolytes to talk about strong and weak acids. So, strong acids ionize completely in water. So, for instance, if we remember HCl, this is not made of ions, this is a covalent bond, it's a molecule. If we put it into aqueous solution, if we put 1 mole of HCl into aqueous solution, we are going to form a mole of chloride ions, we're going to form a mole of hydronium ions. Okay? It is going to completely dissociate. Every single bit of it is going to, or sorry, not dissociate, it's going to completely ionize. Every single bit of it's going to form ions. It's a strong electrolyte. Well, it's also a strong acid because it ionizes completely. Whoops. Let me get that line out of there. When we talk, and we talked a little bit about this in the last chapter actually, we show HCl plus H2O, and this is typically gaseous, this is liquid, and we form an aqueous solution of H3O1 plus and Cl1 minus, also in aqueous solutions. And remember how we talked about the fact that a lot of these were reversible reactions, that you had things coming and going out of the molecular state and ionizing and deionizing? Well, with strong acids, we actually don't show it that way. It is a one-way street. It is a one-way street. So this is a non-reversible reaction. You put gaseous HCl, and if you remember at WTI yesterday, Mr. Laura was talking about the fact that they bubble gaseous HCl through what? Through water, forming hydrochloric acid. Now they have a liquid hydrochloric acid that they can deal with, and they can also introduce the hydrochloric acid to, hey, meet my friend calcium hydroxide. We're going to do this a little bit later today. Okay. So this is shown as a non-reversible reaction because of the fact that it's a strong acid. So do you remember one of the hydrogen halides that we said was a weak electrolyte? There's only one. So hydrogen chloride is a strong electrolyte. Hydrogen fluoride is a weak electrolyte. So hydrogen fluoride is a weak electrolyte. When we take, actually let me move this down. Weird. When we take hydrogen fluoride, gaseous, and bubble it through some water, like they do at WTI in the scrubbers, the end of the stack, this one is reversible. So we get H3O1 plus, and we get fluorine 1 minus. But this one is reversible, and so this is more of an equilibrium state, really and truly, where you're going to have fluoride ions, and you're also going to have molecules of hydrogen fluoride. Common aqueous acids, and they list strong acids, they list weak acids, and if you look at those, you will notice that on the strong acids, is the reaction shown as reversible or not? Nope, just like they said. For weak acids, it is shown as reversible. And so some of the common strong acids we talk about, sulfuric, hydrochloric, nitric, those are the big ones for us. Chlorate, what is that, perchloric acid? We don't deal with that. And over on the weak side, some of the common ones that we'll talk about are phosphoric and acetic. Cyanic occasionally. Cyanic occasionally. But the big ones are really phosphoric, acetic, and yeah, sometimes cyanic. So can you identify, don't yell this out, which one is cyanic acid? You used a base that was a combination of a metal and a hydroxide ion when you made soap. Does anybody remember what base you used? Lye. What is the chemical formula for lye? Sodium hydroxide. NaOH. I'd give you a t-shirt if I had one, but I don't. That's okay. It'll be fine there for years. So when we have a base like this, now this is an ionic compound. If we put it into water and we ended up with a solution full of ions, what process would have occurred? Ionic solution into water, solution full of ions. Dissociation. Yeah, dissociation. So if this dissociated, so if this was a solid and we put it into water and it dissociated into sodium and hydroxide ions, we call the resulting solution alkaline. So this material is a base. This solution is alkaline. And there's a lot of confusion about these words, and I screwed this up myself, so I'm not going to expect you to have it perfect. I'm not going to try to play a gotcha on this. But the compound itself is the base. The resulting solution is an alkaline solution. So alkaline describes a solution. We don't say that sodium hydroxide is alkaline. A sodium hydroxide solution is alkaline, though. Sodium hydroxide is what kind of compound? Well, it's a base.
Whoops. It's base.
And is it molecular or ionic? It's ionic, clearly. Now, there are also molecular compounds that will produce hydroxide ions in solution. And you have worked with one of them that will produce hydroxide ions in solution. NH3 is the prime example. What is NH3 called? Ammonia. And when we put NH3 in water, so this is a molecular compound, we add it to water, we get NH4 1 minus, I'm sorry, 1 plus, and OH 1 minus. What is this product? What's that called? Ammonium ion. Yeah, you've been writing it all year. Or since November anyway. So there's the ammonium ion. And what's this ion? Hydroxide ion. So this is a molecular compound. You put it in water and it forms 2 ions. What is this process called by which we end up with a solution full of ions? This one's ionization, yes. So it ionizes into an ammonium ion and a hydroxide ion. Now, in all these examples, sodium hydroxide, ammonia, what definition of bases are we using here? Hint, we've only learned one definition of bases. You don't have to spell it, but you have to be able to say it. Arrhenius, yes. Arrhenius. So, base strength, just like acids, we can have strong bases and weak bases. Ionic bases tend to be strong, so this is a tendency, it's not a hard and fast rule, but ionic bases tend to equal strong bases because they tend to dissociate completely. Gesundheit. Weak bases just don't yield as many hydroxide ions. So, and that can be because they're not very soluble. Not everything is soluble, remember. And so it doesn't completely break up and dissociate, and so it just doesn't give you a whole lot of ions in solution, so it's weak. But the ionic bases tend to be very strong bases. Okay. Okay, so for the most part, Arrhenius was a fine definition. It was a good working definition for acids and bases. But one of the big problems with it is, and we said this with HCl, it's not an acid if it's in a gaseous form. If hydrogen chloride is in a gaseous form, by the Arrhenius definition, it's not an acid. Because Arrhenius says what? Acids do what? Increase the concentration of hydrogen or hydronium ions in aqueous solution. Therefore, if it's not an aqueous solution, it's not an acid. Well, that's ridiculous and stupid and silly and all sorts of things. So, because of the fact there are substances that behave as acids and bases even when they're not in aqueous solution. So the Bronsted-Lowry definition kind of expands on the Arrhenius definition, and it fixes that up. And in your book, you'll notice that Bronsted has a little line through the O. That's because he's Norwegian or Danish or some place where they make little lines through their O's. But anyway, I want you to think about the word donor for a minute. This is going to be a very important word as we talk about Bronsted-Lowry. Okay. So what I want to know, I don't want you to yell out or anything. I just want to raise your hand if you've ever donated something. Okay, this could be blood, this could be something to Goodwill, this could be a pencil to a friend, $1 for a friend's candy bar. I don't care what you've donated. Okay, you've donated something. What does it mean if you donate something? You give it up, you give it away, you give it to somebody else. Okay. In the Bronsted-Lowry definition, anything that donates a proton to something else is an acid. So, proton donor is the big, this equals acid here. Okay? So, all Arrhenius acids, if we look at HCl, is HCl an acid under the Arrhenius definition? Yeah, we said it is, because it increases the concentration of, we'll just cut to the chase, hydronium ions in solution. Whoops. Okay, but where did the so it's definitely an Arrhenius acid. Where did water get that extra proton? Who donated the extra proton so that water could become hydronium? The HCl did. So the HCl, because remember, a hydrogen ion is nothing but what? A naked proton. It's just a single little naked proton. So we call anything that donates a hydrogen ion a proton donor. Okay? That's the new definition that we're working with. A Bronsted-Lowry acid is something that donates a proton to something else. So, HCl gives up a proton, water takes it, and it is now a hydronium ion. It gets a little weird though, because lots of things sometimes donate protons. You remember ammonia, NH3, stick it in some water, what do we get? We get an ammonium ion, and we get a hydroxide ion. Now, is there a Bronsted-Lowry acid here? There is. What is it? H2O donated a proton. It means water can be an acid in some reactions. That's freaky. That's freaky. So in a Bronsted-Lowry definition, this is a functional definition. So it is all about how they behave in a reaction. So these things only are acids if they're reacting with something else, if there's a situation in which they can donate a proton. Does that make sense? Okay. Yes, ma'am.